Okay, calculus. Today we're going to talk about mean value theorem and the average rates of change. Let's get on with it. Mean value theorem. Sometimes just called MVT for short. We're going to talk about the conditions that have to be met so that we can actually use it. We're going to find C, which could be a number. There are values where the function derivative at C is the same as the average rate of change. Average rate of change should look familiar from Algebra 1, algebra skills. It's your slope. And then we're going to apply the mean value theorem to solve problems or look at problems in context. So let's start with a formal definition. So the theorem actually says if a function f of x is continuous on the closed interval a to b, where a and b are real numbers, and differentiable on the open interval a to b, the same interval, but now it's open, then there exists at least one point c in the open interval a to b where the derivative of f at c is equal to the average rate of change of f on the closed interval a to b. And what does that look like mathematically? That's here. We have the derivative of f evaluated at c is the same as, this should look familiar as y2 minus y1 over x2 minus x1. This is your slope formula. Slope is your average rate of change. Okay, so what does that look like in non-math speak? Okay, so let's say, imagine you're going to get in your car and you're going to drive. You start at point A and you drive to point B. You know your average speed for the whole trip. You just take the distance and divide it by time. Yes, my handwriting's flawless. Don't judge. And this is going to be your slope. Okay. What the mean value theorem guarantees is that at least at some point along your trip, at least once, your speedometer actually read this speed distance over time, which is it will exactly match your average speed at least once. So if the function is smooth, meaning you can draw the function without lifting your pen or pencil, it's continuous and differentiable, then at some point along its curve, the slope of the tangent, that was a terrible tangent. Let's try that again. The slope of the tangent, the instantaneous rate of change, will equal the overall slope from start to finish. Let's say from here to here. What do you notice about these two lines here? They are parallel. So here is a visual example, what I kind of just drew, except this one's got a little more math and more formality to it. So this curve represents some function f of x, right, in red, over the interval a to b. So there's a, there's b. And this is closed, so the function has a value at f of a and it has a value at f of b. The line connecting f of a to f of b is a secant line. It touches the curve at these 2 points. Its slope is the average rate of change from a comma, from a, why won't it write? From a, f of a, to b, f of b. This is the average rate of change. According to the mean value theorem, there is some point C along this curve that when I draw the line tangent to this point, and we do that by finding the derivative, it's going to give me the same exact slope as the secant line. So let's look at an example problem. We'll take a simple polynomial. F of x is x squared plus 2x, and we're going to look at this interval -1 to 2. We need 2 criteria. F of x has to be continuous and differentiable on that interval. So is f of x continuous on this interval? Yes, it's a polynomial. So every value in here will just churn out a real number. There's no discontinuities or any issues. We're good. Second condition, is f of x differentiable on -1 to 2? It is, but let's find the derivative and just to be sure. So f prime of x, using the power rule, derivative of x squared is 2x, derivative of 2x is 2. And on this interval, -1 to 2, this function exists, there's no discontinuities, and it spits out real numbers, and it's nice and smooth. So it is differentiable on this interval. Oops. So now we look to find the average rate of change. So we use our slope formula, f of b minus f of a over b minus a. So that's going to be 2 squared plus 2 times 2, which is also just 2 squared, minus negative 1 squared plus 2 times negative 1, all over 2 minus negative 1, which equals, that equals 3. So we have our average rate of change. This is our average rate of change. To find c, right, we're looking for x equals c that's somewhere in this interval. We need to take the derivative, I don't know why I didn't write that, which is 2x plus 2, and set it equal to 3, which is our average. And then we solve for x. So 2x plus 2 equals 3. That means 2x equals 1. Subtract 2 from both sides. Divide both sides by 2. It means x equals 1/2. So this is our c right here. 1/2 is in between negative 1 and 2. And it is the x value that gives us the tangent to the curve that has the same slope as the average rate of change, the secant line connecting our two endpoints here. Going back to our car analogy from earlier, let's say we have a car, goes from A to B, which is 100 miles, it goes in 2 hours. So all that's saying is, you take 100 miles, you divide that by 2 hours, it's 50 mph, which is what they say right here. That's good. So according to mean value theorem, there's a time where this little guy right here, well, this is kilometers an hour, so let's just pretend it's mph. At some point on our journey, in that 2 hours, at least once, this needle hit the 50 miles an hour spot, okay? If we know our average rate over a continuous and smooth interval, we can be sure that we hit the exact rate at some point in between. Most likely more than once, but for sure at least one time. So if we did that, there are times we hit stoplights where we're below 50 miles an hour. We're at 0. And there are times where we're going on the highway and the speed limit is 75 miles an hour or 65 miles an hour, and we're ahead of 50. But to get from 0 to 75, we have to pass through 50 miles an hour. And to slow down from 75 to 0 at the end of our trip, our speedometer goes back past 50, so it equals 50 miles an hour at some instant. In conclusion, this formula, this equation here, which is essentially an updated version of our slope formula, it's saying that the mean value theorem is about finding the balance point where the instantaneous and the average rate of change, they meet, they have the same exact slope. They won't be the same exact line, but they will have the same slope, the same value. So it gives us a good insight into how functions behave over an interval. Hope this was somewhat helpful. If you have any questions, comments, or concerns, you know what to do. Have a good day.